Ladies and gentlemen, it is an enormous honor to be here. Winning medals shows that you have important friends in important places. Winning the Arthur Holmes Medal of the European Geoscience Union is a very special honor because our science was born in Europe. Europe, whether we like it or not, is the place where human civilization, as we call it, civilization, originated. It originated with the Greeks, and we are all inheritors of that fantastic tradition. And I hope we can keep it. And when I look at all of you here, I am so filled with not only honor, but also with hope that I think we're doing fine. I was asked to talk about whatever I like today as the winner of the medal, one of the privileges that comes. And I remembered one thing that my late friend and Professor Kevin Burke said: when you give a talk, if you don't annoy at least one person in the audience, that talk is wasted. So I'm planning to annoy half of you. And the source of the annoyance will be that I will tell you that geology, the way I learned to do it, is fading, and that it represents a great danger for our sciences, for the sciences of the earth. And I will try to impress upon you the merit of geology as it is done with a hammer, with a pencil, with a topographic map, with a magnifying glass, and a good pair of legs, and of course, a good brain. That is something you can't do without. So, if I can start with the next slide. I don't know how to do it. Yes, are you going to do it for me? Yeah, I use the hammer, yeah, that's right, yes. You see, Hans is right. I'm going to start the theme that I have chosen. This one, right. Oh, this is the gentleman after whom the medal was named. And something that he wrote later in his life about an event that happened to him when he was in high school is the main theme of my talk. So next slide, please. When Lord Kelvin's compression of the duration of the Earth history between 20 and 40 million years caused universal consternation among geologists at the end of the 19th and the beginning of the 20th century, because he was such a great physicist and that he had mathematics at his command. And geologists said, yeah, he's wonderful, but what is it? It's bullshit. We know, but how do we prove it? So when Arthur Holmes was in the last form in high school, he was interested in geology. And when he heard what Lord Kelvin published, he was despondent. And his physics teacher, and Arthur Holmes says he was a brilliant physics teacher, this is Mr. Mackintosh. Mr. Mackintosh said, look boy, here is Edward Seuss's first volume, The Face of the Earth, read it as a consolation. He said, that's the truth. This is the theme I want to emphasize. Next slide is a little show in German as to what a geologist does. Okay, Hagar asked, was will ich eigentlich? What do I want really? And he says, was will jede Geologe? What does any geologist want? And he says, ich brauche nicht viel, I don't need much. Einen Freund, mein Hammer. A friend, my hammer. Einen Traum, a dream. Ein Aufschluss, an outcrop. Eine Liebe, das Handstück. A love, which is the sample, hand sample. ein Ziel and a target, an aim. Verständnis der Erde und ihrer Vergangenheit. Understanding of the earth and its history. Next, please. Well, you know about Karl Schwitzweg. He was a German romantic painter. He painted geologists as a fairly thick fellow. You know, doesn't exude intelligence when you look at him. Okay. And this was the general understanding in the 19th century. The geologist was a collector. And the next slide will show you a mineralogist. The mineralogist didn't fare any better. So, what I'm going to tell you is, how do we start? And I'm going to start in a very mundane way. Next slide. Well, what do geologists look like in the field? Okay, well, in the old days, they looked like this. They were gentlemen. They went out to the field in frock suits. This is Robert Broom in South Africa, looking out for vertebrate fossils. This is one of my students, enjoying his field geology. So there were certain changes in emphasis. Next, this is the new hammer. Geologists use things like that. I didn't dare bring you any other geophysical instruments. They're huge, some of them. But this is the sort of thing that now goes for good research. And if you work in a place like that, publications are guaranteed. And funding is guaranteed. But next slide. You see, this is how we had started. We wanted to know the structure of the Earth. And here is a cross-section from the atlas that Bromme had published for Alexander von Humboldt's Cosmos. And this shows at least his understanding of the crust of the Earth. Well, I mean, you're going to say this is all nonsense. Of course it's nonsense, but it was a step towards understanding. It was something that you could criticize by going to the field, mapping it, and showing that it's not like that, but this is how it is. And when you say this is how it is, you know that what you say is also wrong, but doesn't matter, as long as it is testable. Next slide. Now, this is, ladies and gentlemen, I don't know how familiar you are with these cross-sections. These are by Émile Argan, a gentleman who spoke 17 languages fluently. And when Argan, as a PhD student, sorted out the structure of the Alps, he had nothing but a hammer and a pencil and a map and a magnifying glass. Because he realized the axial plunge from the Ticino Dome westwards lay bare the internal bowels of the Alps. And he said, this is what it looks like. And Albert Heim, in his famous Geologie der Schweiz, says, Argan has sorted this out with a memory and imagination that escaped me. He said. He just couldn't understand how a person could grasp this complication and express it so simply. And you know that the Swiss have published, not too long ago, a wonderful atlas of geophysical data showing at depth the structure of the Alps. Next slide, please. Here it is. That's the structure of the Alps today. That's the structure of the Alps that Argan had published in 1924, actually in 1916. But this also shows the Austro-Alpine maps on top, this is from La Tectonique de l'Asie. You can see that we really haven't improved all that much on it. The details, yes, but not the principle. Because the way he did it, because he looked at the temporal and geometrical relationships of rock bodies on Earth. That's how you understand the architecture of this planet. And that's how you deduce from it, using the fossils it has, using the minerals it has, its history. And, ladies and gentlemen, we are historians. Let's forget that. We are historians of nature. And history in original Greek doesn't mean study of the past. It means investigation. which includes the past. Let's go to the next one. Now, a humble thing that I have done myself. There are some friends sitting in the audience, one is right in front of me, who know this place, Albula Pass. Oh, that's why Christian Dullo is laughing. When I was sent by John Dewey to the Albula Pass, John said, you're gonna map everything, including glacial deposits. And when I went to the Albula Pass, I was so frightened by the complexity. But then I remembered, okay, what I need to do is to go out, map the rocks. This is the mundane part of my job. This is something you all know, but we do less and less of this. Look at the complexity. And let's see from what this simple outcrop observations, a complexity like that, where do we go from that? Next one. You undo all of this deformation. You end up with a sequence like that with two normal folds in a tiny place like the Albula Pass. Then the whole thing gets folded. But in the Alps, everybody thinks when you get first folding, it goes to the north. No, it goes to the south. It's a south-divergent structure. And the normal, look at the normal faults. They couldn't recognize themselves if they saw themselves in the mirror now. Okay, next one. Look at that. Deformation continues. The whole thing separates into two. Okay? And then here, this separation creates little slices. Next one. Look at the slices. Every one of these things you cannot ignore if you want to understand the kinematics, if you want to understand the displacement, and indeed, if you want to understand the physics of how these things have moved. You need to know these details. You can't assume a spherical cow. You need to know the cow. Next. And then, after the whole thing is assembled, the whole thing gets refolded on a huge fold. These are the Großfalten in the Alps. Next. And then you take all these things out, you realize, here, a tiny little place. But this tiny little place gives you a south-divergent structure. And you say, well, I mean, this is not what we had learned in school. Why is this south-divergent? This leads you to the structure, Hercynian structure, of the basement of the southern Alps. This leads you to the fabric of the Hercynian. Next slide. Okay, and then you realize how, because of the normal faulting that in the Triassic and Jurassic opened the Neotethys, that these normal faults had directed, but not individually localized, the big thrusts that go north. The whole thing has been completely redeformed. Look at that. They have been completely redeformed. And you can't pass over these things as mere details, because they are part of the history. Next. Let's go to another planet, Mercury. I asked my good friend Sean Solomon when the Messenger mission started sending radar pictures. I said I would like to receive some of them because I was curious as to what a planet that contracts thermally actually looks like. Because this is what we used to think about the Earth, and we now know it's not. But what does a contracting planet look like? Sean said, no, don't let's do it that way, he said. He said, you come over. As a 2E fellow, we'll pay all your expenses. You stay 2 weeks. You'll look at all the images. I said, oh, what a good idea. So I went there, and to my amazement, ladies and gentlemen, we started seeing structures, thrust faults, orogenic belts. Next one. The blues are structures of shortening. They are folds and thrusts. You look at the literature, you'll read things like wrinkle ridges. I mean, we're not talking about a piece of cloth in a, dish basin. What is a wrinkle ridge? It's something silly. It's an expression of I don't know and I don't care. So I told Sean, I said, look, Sean, I said, geology has names for these structures. Why don't we use them? Previous publications had detected 16 structures of shortening origin, and the geologists told the geophysicists that they could give them a shortening of about 600 meters, radial shortening. And the geophysicists said, no, can't do, we need 10 kilometers. And the geologists said, no, you can't do that. And when we started working on Mercury, as opposed to 16, ladies and gentlemen, we found 5,900 of these structures. Because it requires extensive field experience of geology. You have to recognize these structures. You have to know their siblings on Earth. And when this was done, we've come up with a shortening a bit more than the geophysicists required. Next one, please. Because there is no erosion on Mercury, you can use fault geometries to infer thrusts. From these, you can get shortening amounts. They far exceed anything that's ever been calculated on Mercury. And anybody who has studied the writings of August Buxdorf of Basel, when he mapped the Jura Mountains and discovered the Abscherung, the décollement, and the fault style, you don't need any newer literature to recognize this. That's why I always say, you want to do tectonics, by God, you work in the Alps. If you haven't licked any alpine rocks, you're up shit creek. You have to know the Alps. The only reason is because they've been studied in such excruciating detail by so many generations and by so many rival schools. Austrians hated the Swiss hated the French, and the French hated the Italians. And this mutual hatred was extremely helpful. And the Dutch descended from the north, worked on the Southern Alps, and everybody hated them. But it was wonderful, the things we've learned as a result of all these controversies. See, that's why things like that come easy to the field geologist with good experience. Next one. Okay, now this is the structure of Mercury. And here you have these deep-seated structures. And there you have these shallow structures, décollement structures, that creating the faults and thrusts. And I said, well, why don't we use Stiller's old term of Germanotype and Alpinotype tectonic? I mean, these are concepts that have been invented in central Germany, proved unbelievably useful. Stiller used them for the Rocky Mountains. I said, why don't we use them? People know when we publish these things, because the older people do, not the younger people, because they don't read the old literature. Next one. Now, these are the structures that you see on Mercury, on Venus too. And these structures, ladies and gentlemen, were recognized at the end of the 19th century by Zeus. These are all from Das Antlitz der Erde. If you know these structures, then you suddenly realize that Zeus had sorted out the geology of the Earth. He knew the continents, he didn't know the oceans. He knew the continents. In the continents, no structure that he interpreted turned to be grossly wrong. Not one. That is an amazing lesson. Next. This is Mercury. Again, this is the extensional phase, and we called it the de la Métrie phase. Already in 1775, de la Métrie said, if you have a planet start contracting, the first thing that will happen, it's going to produce cracks in the surface. And then, as it cools, the upper layers will start shortening, and the lower layers will extend. This is what we see on Mercury, these huge basaltic flows early on in the planet's history. Then they get folded. Again, this is done only by looking at the geology in essentially air photos. I mean, these are radar pictures, yes, but you interpret them like air photos. Next. Now we come to a recent paper by my good friend Phil England and Greg Hausman and Nake. They have beautifully looked at, well, they have beautifully mapped a rather nice data set. That is the GPS measurements in Turkey, and you can see Turkey is speeding beautifully westward, and it's moving, and they said, this is so easy to explain if you know physics. Which is indeed wonderful. It'll be so simple. Next. They said, here it is. There is the smooth topography, and this is the gravitational potential energy. They said, you can see that this high air is inevitably going to push Turkey. And if you use a thin sheet analogy, you'll see how it spreads out. Okay? This paper was much lauded by my geophysicist friends, and I said, it really is beautiful. I wish it were true. Because, ladies and gentlemen, Chronos intervenes. Time. Now, this is Turkey about 11 million years ago, late Serra Valley. Turkey had started moving west. We know that. It's all been dated. The faults are known. How it's moving is known. How it's falling apart is known. But the tragedy of it is, it was moving from an area that was underwater, that was under the sea, towards an area that was 3 kilometers high. Well, if you really had that thin sheet analogy, it would move the other way. It doesn't. So, when you look at this, you remember Walter Elsässer. Walter Elsässer told us about, in geophysics, about boundary forces. And you ask yourself, are these things stronger than we think? Next slide. Well, Turkey rose in the east, okay? But we do know one thing about its consequences. Next.